Hello and welcome to the very first video on the Algebra 2 series. Today we'll be going over section 1.1, which covers parent functions and transformations. Before we get started, we're just going to go over how to access the Big Ideas math textbook, which is what we're going to be using throughout the lessons. Big Ideas offers free access to their textbooks, so you can either click on the URL given here or you can check the description for the URL as well. So just choose Algebra 2 and then California first, and then we're going to go to Common Core High School to access the Algebra 2 textbook, because this is the textbook we're going to be using. So just click on the chapter that you want and then the section. So we're going to get started. First, we're going to start by identifying function families. A parent function is the most basic function in a family, and each function in the same family are transformations of the parent function. So the transformated functions will always have similarities with the parent function. So there are four parent functions. The first one we're going to go over is the constant family. The rule is f of x equals 1. And here is what the parent function looks like. The domain is all real numbers, and the range is y equals 1. Next, we have linear functions. The rule is f of x equals x. Domain and range are both all real numbers. The third family that we have is absolute value functions. The rule is f of x equals the absolute value of x. And the graph looks like a V. The domain is all real numbers, and the range is y is greater than or equal to 0. The final family is quadratic. The rule is f of x equals x squared, and the graph has a parabola. The domain is all real numbers, and then the range is y is greater than or equal to 0. So the first example we're going to start off with tells us to identify the function family to which f belongs, and then compare its graph to its parent function. So I've just quickly drawn in the graph of the absolute value parent function, because we can tell by the equation what the absolute values are and the V shape of the graph that it is an absolute value function. So to describe it, we can see that f of x is shifted up from the parent function and that it's narrower than the parent function. The domain is still all real numbers. The range is y is greater than or equal to 1, while the parent function's range is y is greater than or equal to 0. We can see that the parent function's range doesn't cross the y equals 0 line. And then once the graph is shifted up, we can see that f of x does not cross the y equals 1 line, which is why the range is y is greater than or equal to 1. Here's another problem for g. So g of x equals 1 over 4x minus 3 squared. And from the shape of the graph, we can tell that it's rounded, so it can't be an absolute value function. It looks more like a parabola, and the equation has the squares, which means that it's a quadratic function. So I just quickly drew in the graph of the parent quadratic function so that we can compare it to g. We can see that the vertex of the parent function is at the origin, which is 0, 0, but the vertex of g is actually shifted towards the right. So we can say that it's shifted towards the right, and then if we look at the actual shape of the parabola, we can see that g is a lot wider than the parent function. So we can say that g of x is shifted to the right and wider than the graph of the parent function. Then the domain is still all real numbers, and the range is still y is greater than or equal to 0. So now we're going to describe transformations. The first thing we're going to go over is what a transformation is, which is a change in the size, shape, position, or orientation of a graph. Transformation that we're going to talk about is a translation, and this is a transformation that shifts the graph horizontally and or vertically, but does not change its size, shape, or orientation. So now we're going to graph g of x equals x minus 4 and its parent function, and then we're going to describe the transformation. So before we actually graph, we can go over just what we can tell from the equation. So since we have a -4 outside of any parentheses, we can see that this is a translation 4 units down of the graph of the parent function. So now we're just going to graph it to see what it actually looks like. The parent is y equals x, which is a linear function. The slope is 1 since there is no coefficient in front of x. The intercept is 0, 0. And then g of x has a slope of 1 as well. And the intercept is at 0, -4, because when we plug in 0 for x, we get -4 equals y. So now we are going to graph the two functions. We're going to start with the parent function. So we only really need 2 points to graph. We start with the y-intercept at 0, 0. And then we go up 1 over 1 since that's the slope. And we get this line here. For g of x, we're going to go 4 units down. And then we're going to do the same up 1 over 1 with the slope. And then graph the function. Looking at the two lines, we can tell that g of x is a translation down of the graph of the parent function. So that's what we're going to say. The next transformation we're going to talk about is a reflection. It is a transformation that flips a graph over a line called the line of reflection. Any point that is reflected over this line of reflection is the same distance from the line of reflection as the original point was, but on the opposite side of the line. So we're going to try this example. Graph p of x equals -x squared and its parent function, and then describe the transformation. We can see that the parent function is y equals x squared, which is a quadratic function. So here are the typical points from -2, 4, -1, 1, 0, 0, 1, 1, and 2, 4. And we can see this is the x-axis here, and this is the y-axis. We just have f of x equals x squared. Now we're going to graph p of x. Here are the points. We have -2, -4, -1, -1, 0, 1, -1, and 2, -4. So we can see, comparing these two tables, that the y values of p of x are negative compared to the y values of the parent function. So we can see that it's reflected over y equals 0 or the x-axis, and that each point is the same distance it is from the x-axis as it is on the other side once the reflection. So we can say that p of x is a reflection over the x-axis of the parent quadratic function. So now we're going to graph this function and its parent function, and then describe the transformation. G of x equals x plus 3. We can tell from this that it's a linear function because it's just g of x equals x plus 3 without any absolute value bars or any squares. Slope is 1 and y-intercept is 0, 0. The slope of g of x is also 1 because there's no coefficient here. And then the y-intercept is 0, 3, because when we plug in 0 for x, we get 3. Now we're going to graph it. Here is g of x. We have 0, 3 for the x-intercept, up 1 over 1, and here's the graph. And then we're going to quickly graph the parent function. And then looking at these two, we can see that g of x is a translation 3 units up of the parent function, and we can also tell that from the equation with the plus 3 outside of any parentheses. Now we're going to graph h of x equals x minus 2 squared. Parent is the quadratic function y equals x squared, since we have the squared sign on h of x. Here are the typical points, and then h of x. Here are the points for h of x. We can start with the parent function first. Here are the points for the parent function. So we can see from the equation that the x minus 2 means a translation 2 units to the right, because everything in parentheses is flipped, because it looks like we are moving it to the left 2 units, but instead we move it to the right 2 units because of the parentheses. So now if we move each point to the right 2, we get these points. And you can also see that some of these points are actually in our table that we had. So the 0, 4, the 1, 2. So now we're going to graph h of x equals x minus 2 squared and its parent function. So the parent function is y equals s squared, which is the quadratic function. And here are the typical points. And here are the table of values for h of x with the same x values. So now we are going to graph. Here is the points for the parent function. And now we are going to graph the points for h of x. We can see that -2 goes off of the graph that we have. So we're going to go to -1. And 9 is up here. Then we have 0, 4, 1, 1, and 2, 0. We can see from these points that it doesn't look like a parabola because we don't have the whole point for the graph. So there are two ways to graph translations, to the left or to the right. We can plug in more points into the equation to get the y values for 3, 4, and so on. Or we can just look at the equation here and then figure out what the transformation is. Since there's parentheses and then there's -2 inside the parentheses, we can see that we have to move the graph 2 units to the right because everything in the parentheses is opposite of what we do outside of the parentheses. Because it looks like we have to move the graph to the left 2 units, but in actuality, we move the graph to the right. And we can already see that with the points that we've graphed. So this point is moved to the right here, and then this point is now here, and the 0, 0 is now at 2, 0. So now all we have to do is move this point 2 units to the right here, and this point 2 units to the right here. And now we can see that we have the shape of the parabola. So now I'm just going to plot the points that we just plotted, but in blue so that we can see the transformation. And then to describe the transformation, we're going to say that h of x is a horizontal shift 2 units to the right of the parent quadratic function. Here is another practice. We have n of x equals negative absolute value of x, and the parent function is y equals absolute value of x. Here are the points. For n of x, these are the points. As we can see, the y values, again, are negative compared to the positive y values of the parent function. So we are going to graph this. Here is the parent function. And then here is the transformated function, n of x. And looking at the graph, we can see that the x-axis appears to be the line of reflection because every point is the same distance from the x-axis as it is on the other side. So we can say that n of x is a reflection over the x-axis of the parent absolute value function. So the next transformation that we're going to talk about involves multiplying all of the y coordinates of a function by the same positive factor other than 1. So this is either called a vertical stretch if the factor is greater than 1, or a vertical shrink, when the factor is between 0 and 1. So now we are going to graph g of x equals 2 absolute value of x. We can see that the parent function is the absolute value function, and here are the points for both the parent and g. With it graphed, we can see that g of x looks narrower than f of x because there is a vertical stretch going on, since we see the 2 is being multiplied to every factor. So we can say that g of x is a vertical stretch of the parent absolute value function. And when a vertical stretch appears on a function, we can see that it's getting further from the x-axis, and a vertical shrink will cause it to get closer to the x-axis. Now we're going to graph h of x equals 1/2 x squared. Parent is y equals x squared. Here are the points for both. And here is the graph. Compared to the last graph that we saw, we can see that the transformated function is closer or getting closer to the x-axis, which we can say is a vertical shrink. And this is proved by the equation, which has a 1/2, which is between 0 and 1. So we can say that h of x is a vertical shrink of the parent quadratic function. Now we have another practice. G of x equals 3x. This is a linear function, so the parent is y equals x. Since we only need 2 points to make a line, I've added 3 so we can really see what the transformation is like. So here is the parent function, and then this is g of x. We can tell from the equation that g of x is a vertical stretch since the factor is greater than 1. But we can also see from the graph that g of x is getting further from the x-axis compared to the parent function. So we can say that g of x is a vertical stretch of the parent linear function. Now we have h of x equals 3/2 x squared. Parent is the quadratic function. Here are the points. From the equation, we can see that h of x will be a vertical stretch because 3/2 is greater than 1. Here is the parent function, and then here is the transformated function. Since it's a vertical stretch, we can see that it's getting further from the x-axis. So we can say that h of x is a vertical stretch of the parent quadratic function. Now we have c of x equals 0.2 absolute value of x. Parent function is y equals absolute value of x. Here are the points. Here's the parent function, and then the transformated function. Since it's a vertical shrink, we can see that it's getting closer to the x-axis compared to the parent function. So now we are going to graph g of x equals negative absolute value of x plus 5 minus 3. Here is the parent function, which is the absolute value function, and here are the points. The other points, 1, -9, and 2, -10, do not fit on the graph, and we can also see that it doesn't look like the full absolute value function. So we are going to graph each point by moving it from the parent function. So we're going to start with 0, 0. If we reflect it over the x-axis, it'll still be 0, 0 because it's on the x-axis. Now we're going to move it over 5 and down 3 because from the equation we can see that there is a transformation 5 units to the left from the +5 inside the absolute value bars, and then down 3 because of the -3 outside of the parentheses or absolute value bars. So here is the 0, 0. Now we're going to move 0, -1. We're going to first reflect it over the x-axis and then move it over 5 and down 3. And we're going to do that for the rest of the points that we have. And we can see that this lines up with the points that were given from the table. And then we can say that g of x is a reflection over the x-axis, a horizontal translation 5 units to the left, and a vertical translation 3 units down of the parent absolute value function. And whenever we're describing transformations or doing transformations, We always do it from left to right. So now we have a word problem. The table shows that the height y of a dirt bike x seconds after jumping off a ramp. What type of function can you use to model the data? Estimate the height after 1.75 seconds. So first, we're going to identify the type of function that models the table of values, and then we're going to find the height at that specific time. So to figure out what type of function this is, we're going to plot the points on a graph. So here is our graph. I'm just going to add all the points. From the points, we can see that it looks like a upside down parabola, and then it can't be a absolute value function because the points are not on a linear line. They curve down if we connected them, which is what we're going to do right now. And this again proves that it's a quadratic function. Now we're going to find 1.75 seconds on the graph. Go up until we hit the line, and we can see that this is about 15 seconds, and we can see that this is about 15 feet. So we can say that the graph shows the height of the dirt bike is at 15 feet after 1.75 seconds. So we have another word problem. This one is about the amount of fuel in a chainsaw over time. And basically, we're doing the same thing by finding the type of function. And then now we're going to determine when the tank will be empty. So we're going to plot the points on the graph. And we can see from the points that it looks like a linear function. So we're going to sketch in the line. And from the line, we can find 0 fluid ounces on the graph. And then if we look at where the 0 meets the line, we can see that it is at 50. So after 50 minutes, the tank will be empty. Now we're going to graph g of x equals -1/4x plus 5 for more practice. We're going to graph g of x equals -1/4x plus 5 and then its parent function. And then we're going to describe the transformation. Parent function is y equals x with a slope of 1 and a y-intercept at 0, 0. G of x has a slope of -1/4 and an intercept at 0, 5. So here we are going to graph the parent function first. We have the intercept at 0, 0, and we go up 1/1 for the parent function. And then for g of x, we're going to graph the y-intercept first, and then we're going to go down 1 and then over 4. To describe the function, we can see that g of x appears to be flipped compared to the parent function. And then if we flip it over, if we imagine flipping it over the x-axis, then the parent function will be this way. So we can see that's what g of x is doing. If we look at the equation, we can see the negative in front of the 1/4 x. So we can see that it's a reflection over the x-axis. And then the 1/4 tells us that it's a vertical shrink. And this is getting closer to the x-axis. But it doesn't seem that way because of the +5, which moves the graph up 5 units. So we can say that g of x is a reflection over the x-axis and a vertical shrink by a factor of 1/4, and then a translation 5 units up of the parent linear function. Here is the final practice problem. We have g of x equals 3 times x minus 5 squared minus 1. Here are the points for the parent function. So we're going to graph that. Since this is a transformation left or right, we can't really plug in these numbers as we saw before to get the whole shape of the parabola. So we can see that this is actually a translation 5 units to the right. So if we just add 5 to each of the x values first, we'll have -2 plus 5 would be 3, and then so on. Now if we plug in these x values into g of x, we'll see the entire parabola just like the parent function. So we have 5, -1, and then 4, 2, 6, 2, and the other 2 points. And if we graph that, we can tell by looking at these two graphs that g of x is shifted to the right and is narrower, and also shifted down 1 unit. All of this can also be seen in the equation with the vertical stretch of 3 and the horizontal translation 5 units to the right, and then the vertical translation down. So that is all for today's lesson. If you have any questions, you can email second.student.teachers@gmail.com, and all information regarding tutoring, lesson requests, and additional practice will be linked in the description box, so you guys can check that out as well.